Yes, welcome to today's lecture on linear programming as part of the Operations Research course at the University of Mines and Technology. I remain Dr. Bright upon the phone. So in today's lecture, we will look at the two-phased simplest problem, that is solving a particular problem using the two-phase simplex method. So in the past videos or lectures, we have looked at the simplex method of solving linear programming, and we have also looked at the various conditions or situations that we may meet or complications in solving linear programming problems, which we talk about when there's a tie in the pivot column, tie in the pivot row, degeneracy, infeasible solution, unbound solution, multiple optimal solution, and what have you. So today we'll look at two-phase simplex method in solving linear programs. So stay with me whilst we drive towards these important subjects in linear programming. All right, for the two-phase simplex method. So this is actually an alternative method or approach to the big M method for handling artificial variables. So we talk about using the big M method when we are handling artificial variables, right? However, in this case, the linear programming problem is solved in two phases. So in the first phase, we will actually find an initial basic feasible solution to the original problem. And when that is found, it will result in the removal of the artificial variables. So it means that we remove the artificial variables firstly from the first phase. And this, for this, an artificial objective function will be created, which is the sum of all the artificial variables. Then the objective function is then minimized using the simplex method. So we try to still minimize it and using the simplex method to solve, that is the tableau. Then in the second phase, so if the minimization, now we minimize the problem. So if the minimization value of the artificial problem is 0, then it means that all the artificial variables have been reduced to 0. And we have a basic feasible solution to the original problem. However, if there are some conditions, I think we'll look at this. So when that happens, then it means that we can proceed to use, we can proceed to the phase 2. In the case where in the case the minimum value of the artificial problem is positive, then at least one of the artificial variable is positive. Remember that we don't know what the artificial variable is. So we want, at least in the first phase, to remove it. And our main target is that artificial problem or the artificial variables will be 0. However, when you solve the simplex in the first phase and the artificial problem is positive, that is, they do not leave the solution basis, right? Then at least we can say that one of the artificial variables is positive. This means that the original problem without the artificial variable is infeasible, right? Great. So since the artificial variables have no meaning, it implies that the original problem is infeasible and the process is terminated. So when you solve the first phase and the artificial variable do not leave the solution basis, then you end there saying that it is infeasible. So you see that YONGO is different from the big M, where we go through the entire process and later on After solving, then we will now realize that it is infeasible. So in the phase one, it reduces the number of iterations that we have to do if we are to use the two-phase simplex method. So now in the phase two, right, the basic feasible solution found at the end of phase one is optimized with respect to the original objective function. So now we use the original objective function, right, instead of the previous artificial objective function where we were minimizing the solution, right? Good. So now we use the original objective function, and what we'll do is that we see that in the final tableau of the phase one, right, the initial tableau of the phase two actually will change. That is the objective function of the phase two will change because the initial tableau the final tableau of the phase one will now become the initial tableau of phase two. However, we'll change the objective function, meaning that the CJs will be changed, and therefore the CBs, the coefficients of the basic variables, will also change, right? So the simplest method is then applied again. That is, we search for the solution through the iteration process, and we continue searching until there is no better solution, right? So I think it's better to take an example. So let's take an example and let's go through it. So this is a typical example where we want to maximize a function 20x1 plus 10x2, and is subject to x1 plus x2 is called 150. X1 is less than or equal to 40. X2 is greater than or equal to 20. And x1, x2 both satisfy the non-negativity. So we have to create the standard form from the constraints, and then we use the two-phase. So we will move we'll open the whiteboard and we'll do this computation from there. All right, so the problem we have here is to maximize a function z, and the function is 20x1 plus 10x2, right? And this function is subject to x1 plus x2, which is called 150. X1 is less than or equal to 40. X2 is greater than or equal to 20. And both x1, x2 satisfy the non-negativity rule. So we have to create the standard form. So I want to create the standard form by its size. So what we'll do is that we'll first start with the constraints, right? So the first constraint is x1 plus x2, and because it's equal sign, right, we add artificial variable a1 to it. The next one is less than or equal to 40, so we add a surplus or slack variable to it, so it will be x1 plus s1, and it's equal to 40. And we have greater than or equal to 20. So what we do is that we subtract a surplus. This is the second time we are introducing that. Then we add an artificial variable, and we say it's equal to 20. Then we then say that x1, x2, s1, s2, a1, a2, all must satisfy the non-negativity rule. All right, so this is the constraint, right? Good. That has been converted into a standard form. So what do? We said in phase one, we have two. So in phase one, we have to solve the problem as a minimization, right? So solving the problem as a minimization, we minimize the function and we use the artificial variables. Remember that we said we're going to use the artificial variables to create the artificial objective, right? So we are minimizing these two, right? So we need to create our tableau. So we minimize this, and this is subject to all these constraints that we have defined here. Okay, yeah, this is subject to that. So let's draw our tableau and let's solve. All right, so we have our tableau here. Yeah, so at this stage, you should be familiar and you should be very comfortable in drawing the tableau. So we have the CJ, CB, the bases, and we have the BIs. Then how many do we have? We have X1, we have X2, we have S1, we have S2, then we have A1, and the final one, that artificial variable A2. All right, then we have this. And that. So we can now have our CJ, CB, then we have the basis solution. We have the BI, which is the right-hand side, X1, X2, S1, S2, A1, A2, right? Then we have our, it's a minimization. So since it's a minimization, we have the ZJ here, and this minimization. So ZJ minus CJ. If it was minimization, then we use the opposite, which is CJ minus ZJ. But now we are minimizing the function. All right. So the objective function in the new artificial objective function is such that x1 is 0, x2 is 0, s1 is 0, s2 is 0, A1 is 1, A2 is 1, right? Because remember, we said we are maximizing a function A1 plus A2, right? So all the rest are 0. Then when you look at the constraints, right, we had 150 in the first constraint. We have 40, and then we have 20. And A1 comes into solution. S1 is also in solution, and A2 is here. So what's the corresponding CBs are 1, 0, and 1. Okay, so if we are to fill the various contributing the contributing resources for X1, so that will be 1, 1. S1 is not there, was 0. S2, 2 is 0. A1 was there, so it will be 1. A2 is 0. The second one, X1 was available. There is no X2. There was S1. Yes. There was no S2, no A1, no A2. Then X1 was 0, X2 is 1. That the negative X2 is 0. Then 1. All right. So if we are to complete this table, we have 1 by 150 plus 1 by 20, and that will be 170. 1, 1, 1, 0. This should be 1. 1, 1 plus 1 is 2. All this will be 0. B is negative 1. 1, 0 is 1. 0. 1 is also 1. So Zj minus Cj is 1 minus 0 is 1. 2 minus 0 is 2. 0, 0 is 0. Negative 1. 0 is negative 1. 1, 1 is 0. And we expect to have A1, A2 at least being 0, right? Because they are the solution basis and also the S1 being 0. So now we find that the positive Zj minus Cj, the most positive, and that is this column, right? Then we find the leaving non-basic variable, right? So we divide the 150, the pivot column or the in column, with all the values here. So we can have 150 divided by 1 is 150. 40 divided by 0 is infinity. And 20 divided by 1 is 20. And we pick the least value to go out. So that is the least value. And we put out here our pivot row. Yeah. So we circle this to indicate that that's our pivot number. That means that everything revolves around this. So this means that x2 non-basic value is entering into the solution to replace A2, right? To replace A2. So how do we then do our iteration? Yeah, how do we then do our iteration? So that will be our next tableau. That will be our next tableau. Okay, so let's go to our next tableau. Yeah, you should be familiar with this and you should be okay with this. So in our next tableau, right, we can draw the tableau again and say we have this, we have that, we have this, I have my CJZ, CB, I have my bases, I have my BIs, X1, X2, S1, S2, A1, and A2. So we have this, we have that, yeah, we have that, and sorry, I don't need this. So it's CJ, CB, that's the basis solution, that's the BIs, the X1, X2, S1, S2, A1, A2. We have our Z, and we have our Zj minus Cj, right? So we have X, so A1 still remains. Let me use the blue fonts. A1 still remains, S1 still remains, X2 replaces A2, right? And we generate the new, okay, so for X1, still using the optimization, the minimization objective function. So we have 0, 0, 0, 0, 1, and 1. So this is 0, this is 0, and this is 1. All right. So the new BI for X2 is 20 because we calculated it, right? So everything will be divided by 1. So they remain the same. So we have 0 here, 1, 0, -1, 0, and 1. So now we calculate for the 130, the 150, that's the first constraint here, right? Initial value was 150 and the old value is 20 and the pivot number is 1, right? The old number was 1, yeah. So when you compute it will be 150 minus 20 times 1, which is 130. This one will be 1. This one will be 0. 0, yeah. Remember the pivots column, only this will be 1, the rest are supposed to be 0, right? So it comes with practice. S1, when you compute, you get 0. We have 1. I have 1, and I have -1 here. Now, the next value was 0 for the pivot number here. That's the pivot number, which is 1, the pivot column. So this is 0, right? So it means that the numbers remains the same, right? Again, it comes with practice. If you've done it, you see that if the corresponding number on the pivot column is 0, everything remains the same. All right. So that will be 0, 0, and 0. So the ZJ, the Z will now be 130 here. We are minimizing, so it's reducing. It's reduced from 170 to 130, which is fine. This is 1. This is 0, because x2 is in solution. S1 is supposed to be 0 because it's in solution. So keep that in mind. S2 is not in solution, so we have this 1. A1 is in solution. So 1, 1, 1, 1, A2, 1, -1 here, right? So now Zj minus Cj is 1 minus 0. 1 minus 0 is 1. 0 minus 0 is 0. S2, 0 minus 0 is 0. S1 is 0. S2 is 1 minus 0, which is 1. Then A1 is 0. A2 is 0. Sorry, the A2 will not be 0. A2 will be -1 minus -1. And no, sorry, 1 minus -1, and that will be negative. Is it 1? No, it's -1 minus 1, and that's -2. All right, so here we find the positive value, right? So there is a tie here. You can see we have A1, and we also have S1, right? So A1, X1. So we said when you have a tie, you select any of them, right, into the solution. All right, so now when you look at, so we are now breaking the tie, right? When you look at the column here, when you look at the column here, you will see that the pivot column for the first constraint, we have 1, then 1, then 0, right? So if you are going to find the pivot row, then it will be 130 divided by 1, 40 divided by 1, 20 divided by 0. And this one will be 130, this one will be 40, this one will be infinity, right? This means that X1 must go in to replace S1, right? X1 must go in to replace that, right? So that this goes out, right? But our aim is for us to let A1 leaves the solution basis. So assuming we are to go for this column, in the S2 column, we have 1, 0, -1. So what that means is that we are going to get something like, let's compute this on this side. We are going to have 130 divided by 1, which is 130. 40 divided by negative. Was it negative? No, 0. Yeah, 40 divided by 0 is infinity. Then 20 divided by -1 is -20. So you see that from here, right, the most likely value to leave, the least positive value to leave will be 130, which is the A1, because infinity is too large and -20 is not acceptable. We can't take it out, right? It's not reducing the objective function. So the 130 must leave, right? So because of this, to shorten the solution process or the number of iterations, we will go for the S2 column instead of the X1 column, right? So instead of the X1 column. So that means that we will erase that and say that this is the in, right? And we can get rid of all this and say that is 130 divided by 1, which is 130. 40 divided by 0, which is infinity. And 20 divided by -1 is -20. And therefore, this value is the out, right? So we can just clean this tableau. Perfect. All right, so this is what it means. Yeah, this is what this means. So we have to now create the next tableau. We have to now create the next tableau, which is the next iteration. So we have our table or the tableau. We have this and that. So we have the CJ, CB, we have the basis, we have the BIs, we have X1, we have X2, we have S1, we have S2, and we have A1 and A2. So we have this, that, and that. All right. Then CJ, CB, the basis, the BIs, X1, X2, S1, S2, A1, A2, ZJ, ZJ minus CJ, and this to 0, 0, 0, 0, 1, 1. Now the solution basis is S2 goes to replace A1. S1 is here, and we have X2 here. Let me check. Yes, X2. We have X2 here. So all three are zeros. The BIs, now we have 1. Okay, so we have to compute the BI. So the S2 left, so we have to compute that row. The S2 came in and A1 left. So we compute that row, and because it's 1, everything remains the same. So it's 131, 0, 131, 0, 0, 0, 1, 1, negative 1. Yeah. 0, 0, 1, 1, negative 1. So because it's 1, remember everything remains the same here. 1, 1, 0, 1, 0, 0, 0. Then the x2, the pivot number is negative 1. So that means that negative 1 plus, so 130 plus 20, right? 120 minus 1. That's what it means. Minus 1 times 20. So it's 130 plus that. It's 150. 1 plus 0 is 1. 0 plus 1, that. And we have 0. We have 0. A1 is 1 and A2 is 0. All right. So when you compute this, the Z is now minimized 0. So 0, everything is 0. Then the Zj minus Cj, this is 0. 0, S1 is 0. S2 is also 0. A1, 0 minus 1, negative 1, and negative 1. All right. So at this stage, we'll say that the phase 1, right? So the phase 1 is now optimal, right? Why? Because the ZB, right? So the Z for the objective function, that's for the objective function, the artificial objective function is 0. So we have minimized everything in the phase 1, right? So now we move on to the phase 2, right? We move on to the phase 2. So let's keep this tableau and let's move on to the phase 2. So in the phase 2, if we are to draw this in the phase 2, right, before we do that, we need to know that our new objective function is now the 20x1 plus 10x2, right, plus 0s1 plus 0s2. Now, the artificial variables are not in solution, so they are out, right? And this is subject to our objective function, right? This is subject to so it's subject to the initial solution that we have here, right? So it's subject to all this. Let me put it that way. So this remains the same, right? So the new value here, we will place that. The new value here, oh sorry, x1 is not in solution. So the new value here, we will place this. S1, we will place that. And that will also replace that. So there is no new value here. Yeah. So that's what we'll do here in the phase 2. So in phase 2, right, the tableau is, so we have our CJ, CB, and we have the basis, we have the BIs, X1, X2, x2. Then we have S1 and S2. So we have this and that, then this, and now we can fill this and say this is CJ, CB, this is the basis, this is the BI, X1, X2, S1, S2, ZJ. We are maximizing here. So now it's CJ minus ZJ. So keep that in mind. Why? Because we are maximizing the function now, right? And what is the table? What is the tableau on top here? So we have S2 in solution, S1 in solution, and X2. So what is the coefficient for X1 here? 20. That for X2 is 10. This is 0. This is 0. So if you are to replace here S0, 0, and 10. So what are the BI values? From the table here is 130, 40, 150. 130, 40, 150. And we have 11101010110. Okay. So 111 001 010 100. Right. So the Z will just be 1500 here. 00010. Easy. Yeah, it's 10. 000, this is also 10. 000 and 0. CJ minus ZJ is 10 here, is 0, is 0, and is 0. All right, so having this, what then is our in? So we have this as our pivot column, right? Then we divide 130 by 1, which is 130. 40 on 1 is 40. 150 on 1 is 150. So the least value is x2, right? And that will be out. So it means that this is our pivot number. That means that the non-basic variable x1 is entering into solution to replace S1. So our next iteration, X1 will replace S1. So let's do that real quick. So we draw this tableau. The next iteration, we have this tableau. We have this here. This is here. CJ, CB, the bases, the BIs are here. First X1, second X2, then S1, S2. We have them here, that and that. So CJ, CB, our basis, our BI, X1, X2, S1, S2. ZJ is maximization, so CJ minus ZJ. And what do we have here? X1 is replacing S1. So that means that we have S2, X1, X2, right? The values here are 20, 10, 0, 0. So 0, 20, 10. Right, so the new X1 values, remember it was 40 divided by 1. Yeah, so 40 divided by 1, we know what to do. So everything remains the same. 40, 1, 0 on 1, 0 and no 0, this is 1. Yeah, 1 0 1 0. Yeah, so because it's 40, you our next tableau, our next iteration for column is 1 here, so and it's 130. So that means that 130 minus 40, right? So we have this to be 90. 1 minus 1 is 0. We have 0, -1, and we have 1 here. Again, it's positive. This one is 150. So 150 minus 40 is 110. And 0, 1, -1, and 0. So for us to get the Z value, we have 0, 90, 20, 40, 10, 11, 10, and we have 1900 here. 0, 20, 0, 0, 10, -20, -10, that is +10, 0, 0, 0, and this is 0. So Cj minus Zj here is 20 minus 20, 0, 10, 0, 0 minus 10, -10, and this is that. So at this point, you see that this tableau indicates that there is no positive Cj minus Zj value, right? That means that the solution is optimal. So we have an optimal solution here, right? And what that means is that our Z is 1900, right? Unit X1 is, what value is here? 40. X2 is 110, and S2 is 90. There is a surplus here, right? So this is the strategy. So I hope the two-phase approach is well understood. So what we do is that we generate a minimization with the artificial variables, and we use the same standard form of the constraints that we generated. We solve the minimization. So this is a minimization, minimizing Z. So we solve it, and when every Z is 0, that means that the solution, there is we can find optimal solution. So the solution is feasible. That's what we say. Then we now take our phase 2, which is maximizing the function, the objective function without the artificial variables. We solve by using the simplex, and by one iteration, we are able to arrive at the final solution. So I hope this helps and you understand. If you have any question, just drop it on the discussion forum, and we'll be able to address it. Thank you for staying with me. Have a good day.